What? Ready? Yeah. Okay. So, some background first. So, big question in quantum gravity is how does one explain the discrete spectrum of black hole microstates using space-time geometry, maybe souped up with strings and brains, stuff like that. In recent years, there's been some progress in this direction using space-time wormholes. And here it's pictured like a very simple example of a space-time wormhole. It's a picture of a two-dimensional space-time, not a spatial slice. The space-time connects two very different regions, faraway regions of the space-time, and they can be two disconnected, otherwise disconnected regions of space-time. And in a lot of these drawings, we'll think about these space-time wormholes where there's a Euclidean time direction running around the wormhole. So these space-time wormholes have managed to explain some statistical aspects of black hole microstates. It's far from a complete picture of the black hole microstates, but it's at least enough to let us probe the discreteness of the spectrum of the black hole energy levels. So in this talk, we're going to focus on black holes in ADS space, like black holes in a box, and ADS-CFT tells us that these black holes do have, in fact, a discrete energy spectrum. But this is a rather indirect way of knowing it, and we seek a bulk explanation. And to study this problem, we're going to introduce a quantity called the spectral form factor, or here I'll denote it as K beta. And what the spectral form factor is it's two copies of the thermal partition function, where we've analytically continued beta to beta plus or minus IT. T is a time here. And we take this product of two partition functions and we average it. And the averaging can be over some ensemble of systems, or it can be over little windows in the time t. And that's not going to be very important to us in this talk. So why are we studying this spectral form factor? Well, first of all, we can see that it depends on just the energy levels of the system. The late time behavior depends on the small differences between nearby energies. So it's sensitive to the statistics of nearby energy levels. In gravity, Z of beta is a pretty simple thing to set up using the gravity path integral. So Z of beta is computed by a path integral with a asymptotically ADS boundary, periodic in Euclidean time. K beta is just two partition functions. So we have two asymptotic boundaries, but now they have some partially Lorentzian boundary time as well. So it's a pretty simple thing to set up in the gravity path integral, just a sum over geometries with these two boundaries. Another thing is that we know what the answer should be for K of beta at late enough times. This is because K of beta has a universal behavior for chaotic systems, black holes included. So let's discuss this universal behavior that we expect in a spectral form factor.
Chaotic system.
Pardon me?
What do you mean under chaotic system?
It's tough to define precisely for a quantum system what chaotic means. We can have some tests where if the system passes the test, we say it's likely, we would call it chaotic. One of these is the scrambling in out-of-time order correlators. But oftentimes people just say that if a system satisfies this criterion for the spectral form factor that I'm going to tell you, but if it has this late time behavior, then it's chaotic. But there's some other tests which the system should pass, like matrix elements of simple operators should satisfy the Airy state thermalization hypothesis.
Just like it seems it depends on statistics at small energies, right?
Mm-hmm.
So maybe I can design some kind of like integrable system that could have such a behavior.
Yeah. So
it would still have such a
behavior.
Or you mean something else? So it's like it's universal feature for chaotic and could be somewhere else.
Yeah, there is a universal behavior for chaotic systems. Maybe some other systems you can cook up satisfy this, but basically, let's just assume that for the purpose of this talk, that the black holes are chaotic. In ADS-CFT, the boundaries theories are strongly coupled interacting quantum field theories, which we would just expect on all grounds to be chaotic. And there's some other tests besides the spectral form factor, which show whether it's chaotic or not. But it'll take a bit of time to go through all the reasoning.
But then probably ask it differently. So by chaotic, is it something special, or it's really more or less generic?
More or less generic.
It's more or less synonymous to generic in what
Yeah.
you're saying, right? So
Sorry,
it's really non-integrable, right? That's what
Yes,
you mean.
yes.
yeah, related question. So, is it possible to show that, let's say, the fact that, let's say, some out of time ordered correlator saturates some correspond implies some property on the spectral statistics?
That's a really good question. Yeah, I don't know that. I don't know how to do that though.
But it's clear that there should be a relation, or is it just a conjecture?
That's a conjecture. Yeah.
Or they're two, because seemingly they're two independent types of chaos.
Yeah. Roughly the intuition for why systems should scramble, have some maximum exponential growth in the canonical correlator is pretty disconnected from why we expect there to be a rampant plateau.
Yeah, exactly.
It's sort of lore that it should be true, but there's not much well motivated reasoning behind that. It's just sort of empirically we see that all the systems that have the growth out of canonical correlator also have this random matrix behavior that was discussed. A lot of this is just based on like we observe in every system that we reasonably call chaotic, we observe the same behavior. It's a lot of empirical reasoning.
Do we say that even in the context of two-dimensional CFTs, where these observables are capturing the same thing about operator spectrum, the relation between the chaos measured by out of time ordered correlator and the spectral form factor that connection is still not established. It's not clear even.
Yeah, exactly. Okay, so this universal behavior of the spectral form factor that I speak of, it's better defined by talking about a quantity Ke of T. Call this the microcanonical spectral form factor. So we can get that from the ordinary spectral form factor, which we just defined by just fixing the energy with the inverse Laplace transform. And the idea is that for a chaotic system, which we think that the late time behavior of Ke should only depend on just the average density of states, or the microcanonical entropy, and some basic symmetry classes. And the one we'll focus on is whether or not the system is time reversal invariant. And so we'll talk about two cases where there's two, whether the system is time reversal invariant or not. And for these systems, the behavior that we expect from the spectral form factor, or Ke specifically, is the same that we would get if we took that a system to have a Hamiltonian that is a random matrix drawn from an ensemble that has the same symmetry class. So Hamiltonians that have time reversal symmetry or not. And so here I pictured the two cases where the GUE is pictured in blue. That's the Gaussian unitary ensemble, which has no time reversal invariance. And the GOE, the Gaussian orthogonal ensemble, which does have time reversal invariance. So for both of these cases, the spectral form factor starts off large and then decays. And this decay is non-universal. So what we want to do is we want to wait till it's decayed a lot, and then it starts to have some universal behavior. For the GUE with no time reversal invariance, there's a period of linear growth in time up until t equals 2 pi rho of e. And then it sharply transitions to a plateau. It stays flat forever. For the GOE, there's a smooth transition from the ramp to the plateau. There's a series of corrections to the linear ramp. But actually, this function, even though it's sort of hard to tell from the way I've drawn it, it is defined piecewise, where the function behaves one way before t equals 2 pi rho of e, and differently afterwards. So there is a well-defined plateau time at t equals 2 pi rho of e.
So Ke would be like the correlator of two density matrices, something like that.
Yeah, like Fourier transform in the difference of energies.
And these plots are after you average over the ensemble.
Yeah.
So if we're given, a given Hamiltonian in this class, it'll be
There's
some
large noise, lots of noise. But we're always going to think that we're averaging over some ensemble here. Okay, so this rampant plateau, this late time growth and then saturation of the spectral form factor, you think of this as a signature that the boundary theory, or the theory you're studying, has a discrete spectrum. If you had taken a system with a continuous spectrum and computed the spectral form factor, it would decay forever. So that makes this quantity an interesting thing to study in gravity, because if we can compute this late time ramp and plateau structure and see that it doesn't decay, then it should be teaching us somehow how does the theory have a discrete set of energy levels. So we can ask, how do we explain this in a particularly simple model of gravity? So let's focus on what's called JT, or Jackiw-Teitelboim gravity. And it's a simple two-dimensional theory built on gravity. We don't need to know too much details about this theory. So here are some main points that we need to know. So if we compute the Euclidean gravity path integral for JT gravity, rather than integrating over all the Euclidean spacetimes, we only have to integrate over two-dimensional surfaces of constant negative curvature. It's a massive simplification. Another point we need to know, well, we can compute the density of states, this average density of states that we need to know for the behavior of the spectral form factor. And in this case, it's multiplied by a tunable parameter, e to the s naught. So e to the s naught we're going to want to take to be big. Later on, we're going to discuss a limit, the low energy limit of JT gravity, where we can approximate the cinch as linear in its argument, and the density of states becomes this thing. And the last point we need to know is that the JT gravity action has a term which is proportional to the Euler character of the manifold you're evaluating it on, multiplied by s naught. So what this does is it suppresses contributions of surfaces with higher topology. So the more negative your Euler character, the more powers of 1 over e to the s, or roughly 1 over rho of e, surface is suppressed by. So here we've pictured just an example contribution to the spectral form factor. We've got two boundaries, and here we've added two handles. So it's a genus 2 surface. The Euler character is -4. This would be suppressed by e to the -4 s naught.
So the S0 is like the zero model of Leland, like in string theory.
Pardon me? Oh, yes, it's like the string coupling roughly, e to the -s. And so this means we have a nice topological expansion. We have a genus expansion.
But that rho v, that comes only from trivial topology?
Yeah, rho v you compute from the trivial topology, but roughly we're going to study these higher genus surfaces, and we'll find particular contributions that look like they're suppressed by 1 over rho to a power, not just e to the -s naught. So it's, yeah, we'll discuss that some more. Okay, so if we're studying the spectral form factor in JT gravity, let's start by computing the simplest topologies. So the leading topologies would just be two disconnected disks. And in JT gravity, the disk topology is an analytic continuation of the two-sided ADS black hole. So we have two analytically continued black hole geometries, and it turns out this contribution just decays forever. So that's the initial non-universal decay in the spectral form factor. The next order we can go to is a wormhole, a cylinder topology with Euler character 0. In JT gravity, or even in higher dimensional gravity, we can construct a cylindrical solution which is a certain quotient of the black hole spacetime. But the details about that aren't important. The point here is it's a wormhole that's a cylinder, and it gives the linear ramp in the spectral form factor. So how does it do that? Well, it has a suppression of e to the 0 s naught, so this it's of order 1. But then you get a factor of t, because for these geometries there's a 0 mode corresponding to rotating the left boundary with respect to the right. So there's roughly t ways we can rotate them if the boundary time is t. So this gives something proportional to t. This is the ramp in the picture I had before. So higher genus surfaces come with powers of e to the -s. Roughly that's 1 over rho of e. And so we can ask, could the series of higher genus corrections explain the plateau in the spectral form factor? Now there's a problem with that, which is that in KE, the transition from the ramp to the plateau is a sharp thing. It happened very suddenly at t equals 2 pi rho of e. We can understand that what's going on a little bit better by Fourier transforming KE with respect to t. Let's take the Fourier transform variable to be delta e. The Fourier transform has a behavior, I neglected to write a factor of I here. It should be e to the I times some number times e to the s times delta e. So it's oscillating in delta e with frequency proportional to e to the s. So that is a non-perturbative effect in e to the -s. This is not something you'd be able to compute from the genus expansion. It's non-perturbative in the genus expansion. So it doesn't look like we'd be able to explain the plateau by sum over higher genus surfaces. We'd have to do some sort of Durrell summation or something complicated. But there is a simplification if we look at k beta rather than Ke. The idea is that K beta includes a sum over energy windows. And because the time at which this transition is happening is depends on the energy, summing over the energy windows can smooth out this transition, giving us a nice smooth function which has a genus expansion. And we're going to look at cases where we'll be able to get, in fact, a convergent genus expansion for K beta. So it starts off growing linearly with a ramp, but then at late times it smoothly transitions to a plateau.
Then you can transform back.
And then you can transform back. Yeah.
Question. So is the genus expansion Borel summable?
In some simple cases, yes, but I don't want to make any general statement.
But even if it's not Borel summable, you can still do the Borel summation and do this. There's some kind of more sophisticated technique to do the summation. Have people tried that?
People have.
And try to explain the plateau that way.
Yeah, we tried that a little bit, but in fact, I kind of want to think about K beta as something like a Borel transform of Ke. And so you start with something that would have an asymptotic series and get a convergent series. But it's like in this case, the Borel transform itself is the physically interesting thing. So you don't need to go back to that.
And also, just another question, going back to the previous slide. So the trumpet geometry with general beta and T, this is a complex geometry.
Yes.
Is it consistent with the Kontsevich-Graham criteria?
Oh, yes. That's an interesting question. I can actually go into more detail afterwards. We have to think about that a bit.
It's also not a solution.
It's not a solution.
It's a solution at fixed energy, but not a fixed beta. That's some details I didn't want to get into. Okay, so let me discuss this convergent genus expansion, which will be our main focus. So remember that K beta was defined in terms of Ke Ke was defined by the inverse Laplace transform. We can get back K beta by Laplace transform Ke. So you just basically take Ke, integrate over the energies weighted by a Boltzmann factor. And now, if we plug in our ramp plateau formula for Ke, let's just focus on this GUE class with no time reversal invariance. We can plug in the formula, which is this ramp plateau. Here I've written it as minimum of T over 2 pi, that's the ramp, and rho of E, which is the plateau. This is a guess for K beta. Now the problem is, this includes a sum over energies where rho is small. That's when the plateau happens very early. And we may expect large deviations from this simple random matrix theory prediction, the ramp and plateau. But actually, we expect this to be exact when the density is large and the time is large. So we can do something nice, which is we can take e to the s naught to infinity. That's the prefactor in front of the density state. So the density of states gets large for any finite energy. And then we take the time to scale as e to the s naught. So we take this combination tau, and we pull tau fixed. Let's call this the tau scaling limit. We'll refer to that later on. So in this limit, this expression becomes exact. And roughly what's going on is that all contributions that don't grow enough, don't grow quickly enough in time are killed. And we get a simple answer. That's just a leading growth in time. And it's a side comment for those who know what this means. This should apply to all double scale matrices, not just JT gravity. So let's take 2 examples. One will be this low energy limit, the Airy limit, I'll call it, of JT gravity, and then we'll also talk about JT gravity itself. So here, the point is that you can just do the integral that I had in the previous slide, do the energy integral of the ramp and plateau. And we get a nice function, which is the error function. So the error function will start growing linearly in time. We expand for small argument, but at late times, the error function flattens out. So this has a convergent expansion, giving the ramp leading order, but all these corrections give us the plateau at late times. And this, in fact, matches with some exact formulas that have been derived for this model. For JT, the expression is a bit more complicated. The first 2 terms in this series are the same, but the next term has a correction. But the main point here is that it also gives a convergent series in tau. And here we want to think about the series in tau as coming from a topological expansion. Every time we get 2 more powers of tau, that comes from another handle on the surface. We'll talk about that more.
So I'll try to ask it. So why there are no topological corrections to spectral density itself? Why?
Oh, those become. I have to it'd be hard to explain in detail right now, but those are roughly go away in this tau scaled limit.
Yeah, I understand, but okay. So you choose by this limit, but in principle,
They're for finite tau or for finite e to the s naught, those will be there, and they make the exact function very, very complicated.
but exactly the effects which kind of don't grow
Yeah.
with time. And this way.
In fact, those can be taken completely into account in this model. So you can write for outside of this limit the exact formula, and it's just they just change the free factor basically. Okay, so let's make some comments about this genus expansion for the plateau. So the series in tau corresponds to this genus expansion where tau appears to the power 2g plus 1. At genus bigger than or equal to 2, naive power counting would say that you might get a power t to the 3g. Now that doesn't appear in a formula. We actually get the highest power of t is t to the 2g plus 1. So this implies that there's a lot of cancellations between these higher powers of t. So the answer you're getting is not just saying, oh, there's a naive power counting argument for the answer. It's a bit more subtle, and this has been studied in some recent papers. And maybe the most important point for us right now is the following. So naively, there's no genus expansion in this GUE ramp and plateau. It's a linear ramp with no corrections, and it has a plateau with no corrections. But we can do a little bit of a strange thing here, and let's write the minimum using a theta function, and then expand the theta function as a series of derivatives of delta functions. So plugging all this in and setting x equals t and y equals rho, we get a series for k e of t in powers of time, where the coefficients have derivatives of delta functions of rho of e. So there's a way which will make a little bit more precise, which is of thinking about these series of corrections, these higher genus terms, as being it's coming from zero energy corrections. So if at finite energies the ramp and plateau is correct, but at zero, if you look at zero energy, that's in fact where the density becomes small and the plateau happens at an early time. Then there's a series of perturbative corrections. Okay, so our goal is going to be to explain this genus expansion with K beta in Jackiw-Gravity specifically. And we're not going to be able to give a comprehensive explanation, but we'll be able to say some things. But we're going to take a little bit of a detour first. Rather than studying the genus expansion for K beta, let's study a different genus expansion, just to get oriented, actually. And it'll turn out to be very helpful. And this genus expansion is only appears in the GOE class. So remember there, the spectral form factor didn't just have a linear ramp, it had a series of corrections. And a series of corrections is going to correspond to a genus expansion. Ordinary JT gravity only includes orientable surfaces, and that is related to the fact that it's the GOE symmetry class. We can make it the GOH symmetry class by allowing non-orientable spacetimes. So these non-orientable spacetimes will give us a power series for KE, which is a series in T over rho. So this is the thing, this is what we expect for the spectral form factor, where we include non-orientable surfaces. But rather than study this first in JT gravity, let's talk about a very different looking system. And this system is going to be chaotic billiards. So consider a particle moving in a stadium where the classical motion is chaotic. So I've drawn a stadium and the particle, here's the sample trajectory in red. For these sort of systems, just a particle in a two-dimensional stadium, you can use a refinement of the path integral to write a formula for KE. It's called the Gutzwiller trace formula. And so what it is we take a sum over orbits for one copy of the system, orbits gamma, and orbits gamma prime for the other copy of the system. We have e to the I action left minus action right, because spectral form factor has one copy with plus IT and minus IT for the other. And then we have this A here is like the one loop determinant, but we've assumed here that gamma and gamma prime are give similar one loop determinants, and that's something we make. And here I've written it for h bar equals 1. So the semiclassical limit, which is where this formula is valid, is going to correspond to high energies E. So these orbits that we sum over, they're going to have energy E, where E is the E in KE, and they're going to have an average period T. So the idea is that for long times, these actions are big. And when we do any sort of averaging, unless these phases cancel out or the actions are correlated in some way, then averaging will kill all these contributions. So we're going to focus on pairs gamma, gamma prime, where the action difference is small. So the leading order thing is sort of obvious. We just take orbit left equals orbit right, gamma equals gamma prime. And in time reversal invariant cases, we can have gamma prime be the time reverse of gamma. If we sum over these, it turns out to give this linear ramp in the spectral form factor. This is due to Barry. The factor of t comes from something very similar to what we saw in the wormhole, which is relative time translations between the left and the right.
So I go to this was so you are trying to reproduce these results from classical billiards now.
Yeah.
So how do we see this GOE or GOE or?
Well, we'll see that, and it'll be pretty clear in a moment why there's a distinction.
No, I meant like why do billiards have GOE or GOE?
Oh, it's just is the theory time reversal invariant or not? So like an ordinary billiards, it's going to be time reversal invariant. But if you have like couple it to magnetic field or something like that, then it won't be.
I see. And Barry shows it.
Yeah.
Why is the action? I'm a little confused. So the thing you had before was just energy times time. Right. And so now what's the action for the billiard?
Well, this is the action for the billiard would be whatever. It will depend on the theory, but roughly it's going to be energy times the period of the orbit.
Can I think of this like, you know, a Schrödinger pattern? Like I have stereo, it's like some surface, and my particle is confined to that, and just study Schrödinger problem.
Yeah.
And I just want to find energy spectrum of this.
Yeah. But this is just using the pattern real quick. Okay. To get back to your question, so if you have a sort of complicated theory with this magnetic field or whatever, the action is not just going to be the energy times the period of the orbit, but in the simplest cases, there's a case where that formula is in fact exact. It's called the Cellwork trace formula, where you study a particle on a quotient of hyperbolic space, and there the action is literally just energy times the period of the orbit, and it's very simple. So talking about orbits with similar actions means talking about orbits with very similar periods. So we can just think about that to keep things simple.
You sum over distinct orbits.
Distinct orbits, yes. And
So
so
in the super trace formula, you sum over not only distinct but primitive geodesics, right?
oh, they can repeat as well, but that's a bit. Those are not important for anything we're going to talk about this before this. What I want to do is make an analogy to the wormhole and this Barry pair. So roughly, the idea is that we think about the boundary in the wormhole as like where an orbit lives. In the wormhole, the left boundary follows the right boundary. So here is sort of close to here. Here is sort of close to here. And so the wormhole represents two identical orbits following the same path. And we'll find we'll make this analogy a bit broader in a moment. Okay, so that explains just the ramp in the spectral form factor. What about the series of corrections in the GOE? So to do this, we have to focus on pairs of orbits which closely follow each other, except for some small off-shell regions called encounters. And so here's the simplest example. It's called a two encounter or the Sieber-Richter pair, named after the people who discovered this. So the idea here is that let's follow the black and the red orbits. They follow each other in the same direction here, but over here, so the black guy crosses itself and the red guy narrowly avoids itself. This is the encounter region. On this side, they're going in opposite directions. We only know that there's pairs of orbits like this with almost identical actions, where the actions cancel along this stretch, if the theory is time reversal invariant, because they're going in the opposite direction.
So do I assume now there's some kind of interaction between billiards?
So this is just a picture. So we're looking at long times and we're assuming that the motion is ergodic. So there's all kinds of orbits that narrowly cross themselves at small angles or narrowly void themselves. These orbits are known to exist for sufficiently long times if the system is ergodic.
Where's the off-shellness?
The off-shellness I'll get to in a second. So let's talk about how can we parameterize one of these Sieber-Richter pairs. So there's a time I'll call t stretch of say this period of this stretch of the orbit. So the total time is constrained to be t. will fix the time here. So then the time here plus the time here plus the time here is equal to t. So there's one parameter here, t stretch, which just tells us that time. Within the encounter, we want to parameterize what's going on by two phase space separation variables s and u. And here we're assuming the Billiards is 2D, so there's only two phase space separation variables. And here I've drawn a little cartoon. This isn't quite right. This is a picture of the orbits in configuration space, not phase space. But roughly, u represents the unstable separation direction of phase space, and that grows along the encounter. So as these two orbits deviate, their phase space separation variable u grows. But this orbit converges to this one, and the stable separation variable decays exponentially. And so what we're doing here in this region inside the encounter is we're treating the equations of motion around to linear order in small deviations of these two orbits. So in this linearized regime, these variables s and u grow or decay exponentially with the Lyapunov exponent lambda. So this is what's expected for any of these quadratic systems. And now, what are the details we need to actually compute the contribution of this sort of pair of orbits? We need the duration of the encounter in terms of s and u. T encounter, it's like log s of c squared over su. C squared is like a cutoff on the validity of this linearized regime. The answer should be insensitive to that in the semiclassical regime, which it will be. But let's sort of remember that we needed some sort of cutoff. The action difference of these pairs of orbits is SU. So this is why it's slightly off-shell. We have to integrate over S and U.
Sorry, C would be like putting a measure, it's like a metric on what it means to be separated or something like that.
Yeah, so it's like C we can think of as like how far do we integrate S and U? If we integrate them to be too large, then the linearized regime breaks down.
So that's this is the only range you have, as long as this
yeah,
conversion, and then eventually you expect this not to depend on C.
Yeah, but it turns out that the answer is coming from small s and u, so it's insensitive to the cutoff. So we did this just we didn't have to think about it very hard because it'll turn out that the answer doesn't care. And then the final thing we need is that what's the probability to find a pair of orbits like this for a fixed s, u, and t stretch? That can be determined by ergodicity. Be dt stretch, ds u, roughly over rho of e. So that's 1 over the volume of phase space.
So just to make sure, you're saying that this action difference depends only on the encounters, or
only on the encounters, because they're following each other basically exactly outside of the encounter. So if we put this all together, there's a big nasty formula, but the pieces are relatively simple. There's a relative time translations between the two orbits. There's the volume of phase space suppression for what's the probability that the encounter happens. There's integrals over S and U. There's the T over 2T encounter places where the encounter can happen along the orbit for fixed S and U. There's an integral over the length of the stretch. That's its maximum length is T minus 2T encounter. And there's this action waiting. And putting all that all together, we find something like this. And we have to do this SU integral. Times EVI-SU. So there's a leading thing which would give a power T cubed, but it depends on T encounter. That actually integrates to death and cancels. So we're left with this subleading term with the -1, and then we just get a delta function type integral. We get T squared times minus something over rho. So just to say the main takeaway points, there's a minus sign which is going to be important because these things will have to cancel. The minus sign comes from the subleading correction. There's a 1 over rho just because for an encounter to happen, the probability is suppressed by the volume of phase space, and this T squared comes from counting various zero modes to be encountered. So that was for this GOE case. This gives the first correction to the ramp. But for a moment, let's talk not about the GOE case, but the GUE case. Then we have to consider only these pairs of orbits where they're following each other in the same direction along all these stretches. So the leading sort of encounters that have this property I've drawn here, where there's two encounters that are widely separated and a 3 encounter. And you can see that along all these stretches, orbit left is following orbit right. So these can contribute to the GUE ensemble. And it turns out, if you try to compute their contribution to the spectral form factor, very similar computation to what we just saw. and they give the same answer except up to a sign. So because there's two encounters here, there's two space-based volumes suppressing it. The 3 encounter is even more unlikely to happen than a 2 encounter. That also gives us 1/2 rho squared suppression. And there's t cubed instead of t squared in this order. But now it turns out, so I just told you they give the same answer up to a sign. So when you add them, they cancel. So this is saying that in the GUE, there are no corrections at order t cubed from encounters. In the GOE case, there will be some extra encounters at this order, which would give a t cubed over rho, and they wouldn't cancel. It's been shown actually that at higher orders, to all orders, in the GUE class, all the encounters cancel. And in the GOE class, the remaining, the extra ones that appear only for the GOE, give the correct series of corrections to the GOE spectral form factor.
Sorry, you said it, but how is the sign determined?
Oh, this sign, so
you have some general rule, like how the sign is determined depending on how they encounter?
So the sign, so here there's like a sign which is just came out of the calculation.
Yes, yes, the -1.
Yeah.
Yeah.
So roughly in 2 encounters,
Yeah.
there's 2 minus signs that cancel. For the 3 encounter, there's a minus sign that doesn't cancel.
So there's a general rule for the more general case.
Yeah, yeah. So the calculation is very simple generalization of the rules we just saw for the 2 encounters. Okay, so we want to make a rough dictionary between encounters and wormhole geometries. And roughly, what we want to do is say that a geometry is like an orbit. If in the orbit we have sections of the orbit, of orbit left and orbit right, which are following each other, like these stretches. Those correspond to geometries where the left boundary and right boundary follow each other closely, similar to the wormhole. But then we also have inside the encounter region, multiple segments of the left boundary and right boundary can become mutually close. So here I've drawn this picture of the encounter. Here's one of the orbits, here's another orbit. And let's twist around the top here so that we can see that there's a region in between the orbits. And we imagine that the geometric picture is that we fill out this region. So along here, the black boundary is close to the red boundary, but then there's this region where they're all sort of near each other, and they sort of switch where they're close to. The red boundary starts by being close to this segment of the black boundary, but then it switches to being close to this segment of the red boundary. So, as I mentioned earlier, for JT gravity in the GOE ensemble, we include non-orientable surfaces. So that means that encounters that only contribute to the GOE, like the 2 encounter we just studied, those correspond to non-orientable surfaces. And so let's study for a moment JT gravity on the surface that you'd get by thinking about the 2 encounter. So it's the simplest non-orientable surface contributing to the spectral form factor. What I've drawn here is a picture. So in JT gravity, we include only constant negative curvature surfaces. So this is a picture of the hyperbolic disk, and we've cut it out in some ways and made some identifications. The identifications are indicated by these arrows here. Gluing along these identified edges makes a surface that's a wormhole with a cross cap on it. And then I've drawn here some geodesics. These are all circular geodesics: B1, B2, A, and A prime. Only 3 of them are independent on this geometry. And we're going to see how this geometry represents this 2 encounter. It's a little bit misleading because it's a Euclidean picture I've drawn here. We're supposed to analytically continue, but that's a bit hard to draw. Oh, and the last thing I want to mention is that the asymptotic boundaries are way out here where these wiggly lines are. And the asymptotic boundaries roughly follow these B geodesics. And these B geodesics, turns out if you study the spectral form factor, they have lengths which are proportional to time. So we can roughly think about the B geodesics as where the orbits live instead of the asymptotic boundary. And so what I've done here is I've taken the picture from the previous slide and I've cut out the region bounded by the B geodesics. So here's B1 in red, and B2 is the dotted black line. And here are the identifications we need to make. We glue this to here, we glue this to here. So this surface is supposed to represent a 2 encounter. Again, it's a Euclidean surface, so it's a bit misleading, but we can see that this roughly looks like the encounter I drew earlier. So out here, because this is a hyperbolic geometry, out here there's a lot more volume. So these 2 segments are following each other for a while. So this follows this for a while, this follows this for a while, and so on. But in this middle region, all of the red boundaries and black boundaries come close in a way that mimics the two encounter. And it's less obvious from this picture, but A and A prime turn out to be very closely related to the S and U phase space variables. So we can compute if we study the spectral form factor on this surface, the path integral can simplify to a form where it looks like you're integrating over pairs of orbits with lengths that are like B, or they have periods T, which is proportional to B. And the action difference is proportional to E times the difference in the periods, or square root of E times the difference in the lengths. And it turns out in the Lorentzian signature, you have to give these guys a small imaginary part, but that's not very important. If you process the formula a little bit, the path integral for Jackiw-Teitelboim on the surface, as an integral over the lengths B and B1 and B2, looks a lot like looks exactly like the integral we've written for the two encounter, except that the T encounter formula is corrected. So for small delta S, that means T1 near T2, that's the region where the encounter approximation is ordinarily treated. This cinch can be linearized, and we get the formula we had before for T encounter for orbits. But now we have some control over the large delta S or large period difference regime. So that's where we have to cut off the encounter picture. So the point here is that if we want to compute KE, we won't really need that large period difference regime, but it's going to be important when we study K beta. Oh, this is I'm going to skip this slide. It's necessary. Okay. So at higher genus, at genus 1/2 in JT gravity, we found a surface that resembled the two encounter. It gives the same answer. The whole path integral reduces to the same integral as we saw for the orbits. We expected this picture to be valid at higher genus, as long as we're at high energies in the spectral form factor. There we can make a lot of approximations. Like the period of the orbits need to be approximately the same. But at low energies, so remember that K beta includes the sum over energies weighted by the Boltzmann factor. That includes a sum where the energies are small. The encounter approximation becomes invalid. So that's because the action difference between the two orbits is proportional to like E times the difference in the periods. So if the energy is very small, then the difference in periods can be large. So there, you don't have to just consider orbits that mostly follow each other, like encounters. Basically, any sort of pair might be able to contribute. So there, it looks like we might be out of trouble. But we saw just now in JT gravity that we had some control over this regime where the periods are very different, and it still looks something like encounters. And so the point that I want to explain in the last bit of this talk is that these low effects at low energy, where the calculation becomes very quantum, rather than looking at semiclassical computation where you have small deviations around the encounter, you have to look at large corrections from very different orbits. These sort of low energy corrections are going to disrupt the cancellation between encounters. And so rather than the two encounters canceling the three encounter, because they have some corrections at low energies which are different for the two encounters, they no longer cancel, and you get the correct formula for K beta. And to explain this, we're going to back off a little bit from JT gravity, which is a bit complicated. Well, that's not very complicated, but we're going to study an even simpler model, which is just the low energy Airy limit of JT. And the reason is the geometries are simpler. So let's discuss why they're simpler. The first thing we want to do is we want to say, let's take any wormhole geometry in JT. We start with JT and we'll take a limit. It has these asymptotic regions bounded by these B geodesics, which I drew on the two encounter example. We want to just take these off and consider a piece in the middle, which is where all the higher genus stuff lives. We can write a formula for K beta, which is an integral over the B's. There's some action coming from these asymptotic regions here, which depends on B1 and B2. And there's something that involves just the sum over all these higher genus surfaces with fixed B1 and B2. Call that DG. It's the volume of moduli space at genus G. So to get this Airy model with the square root of E density of states, we want to take beta large. In doing that, we scale beta to be very large. We focus on b's, which are very large. So roughly, we can, in this limit where we take beta to be large and do some rescaling, we find that the k beta for the Airy model is like the same integral here, these asymptotic regions here, but now we have a modified volume of moduli space, which is just the limit of the ordinary volumes, and where the b's are taken to be infinitely long. So we're studying basically surfaces where the boundary lengths are very long. So why are those simple? So the idea is that we're studying surfaces that have constant negative curvature. Inside this region here, these boundaries are geodesics. So the Gauss-Banate theorem tells us that we have a constant curvature K and geodesic boundaries. The surface has a fixed area proportional to chi over the curvature. So if we have a fixed area surface, but the boundaries are becoming very long, then they have to become very thin. They look like thin strips. So like imagine a rectangle with fixed area, but where you take the two of the edges to be very long, the other two have to be very short. So in this limit that we're studying, the geometries become very thin strips. And there's a very simple way to describe the moduli space of these surfaces, these thin strip surfaces, due to Kontsevich. And so because these surfaces are very thin strips, they can be represented by a ribbon graph. Here it turns out all we need is cubic ribbon graphs. So here I've drawn a cubic ribbon graph where one of the boundaries, B1, is pictured in red. The other, B2, is pictured in black with the dotted lines. So the geometry we're focusing on, so the geometry is just what lives inside the ribbon graph here. It's thin strips with these cubic vertices. And so for every graph, we can give the edges of the graph, here there's 3 edges, we can give them a length. So we can parameterize all the surfaces by saying, what graph does it look like? And on this graph, what are the lengths of the edges of the graph? And the integral over these geometries simply just turns into integrating over the lengths of these edges of the graph with a flat measure. Subject to the constraint that the black boundary has like B1 or B2 or whatever, B black or whatever I've defined it as, and the red boundary has also a total fixed length. And so let's talk about the two-encounter moduli space for these graphs. So this is the same genus that we saw in JP gravity, but now we've taken the limits and we've drawn all the graphs that apply at this genus. So let's first focus on these first 2 graphs on the left. They have 2 edges that have the black boundary following the red boundary. And then they have this, either the red boundary following itself or the black boundary following itself. So these sort of edges correspond to stretches between an encounter. And this thing in the middle here, we're going to think of as living inside the encounter. So here I've drawn this region of the graph in a little bit of a different way. There's the black, there's a stretch, there's a stretch, there's a stretch, there's a stretch, and there's this red region. If we shrink this red edge, it resembles the encounter picture. But in these graphs, what we're able to do is resolve the encounters for finite differences of lengths. So if differences of lengths are large, we can have a large region within the encounter. So these, when we do this shrinking, these resemble the 2 encounter. But there's these other graphs as well. Oh, crap.
Do you happen to have the
I think I forgot. My computer usually lasts a lot longer than this.
the USB? I have a charger on my.
Oh, yeah, that would be great if you
I have
spaced down.
this one, I don't know if it's long enough.
Oh, is there a plug right around here? I think there's a.
There's one on the left. I think it's what.
Thank you so much.
Yeah, of course.
Okay, so where did I put the? Here we go. Okay, so hopefully it's clear why these graphs resemble the encounters when we insert these edges. So there's these sort of funny looking graphs on the right. It's less obvious, but those also correspond to the 2 encounter, but in a sort of extreme regime of the 2 encounter where it looks less like an encounter. And so it's not been really important to understand this, but we can start with this picture of the geometry I've drawn that hopefully looks like a sort of deformed version of the encounter. And if we make the identifications we need to do, we identify this edge with this edge, we have to twist it around so that this region here becomes this region here. And then we make this identification like this. we get a surface which looks like this. So in an extreme limit, this surface resembles this graph here. So the main point is that the graphs.
Sorry, just to be sure. So you have two geodesics in the original picture, the B1 and B2. They have geodesic length B1 and B2. Should I think about the dotted black as forming one of the geodesics?
Exactly. Yeah.
And then the other, the red, to be the other one.
Exactly.
Okay.
Yeah. So here it's like the one of the geodesics, the black dotted one. There's only like one stretch where the red follows itself, and then there's this region where the red boundary goes off and follows itself for a while. And so it's a bit difficult to explain in detail, but this second set of graphs is also part of the two encounter, and including all these graphs, we get precisely the two encounter answer for KE of T.
Why was it called Airy limit?
So that's because it's some historical thing. It's because not the spectral form factor, but some other quantities related to the spectral form factor turns out to be the Airy function in this model. Some like
Airy function. What is the variable?
It's like the energy. So it's a determinant of energy minus Hamiltonian. It's the Airy function in this case. It's a function of the energy.
Sorry, would this then be related to like the Einstein or Ronson topological recursion?
Yeah. So topological recursion would. So this is in a limit where the topological recursion applies to this model as well. This is like a different way of computing the modulus, the volumes of the modulus space. It's an interesting question to understand how they're related. So we saw that we needed to do something a little bit strange for the two encounter to translate these graphs into encounters. There's some graphs which sort of aren't obviously part of the two encounter, but they were if you think about it hard enough. So let's now focus on the GUE symmetry class at genus 1. This is where we expect to find some correction to K beta when we find where in KE everything should cancel. So I've drawn all the graphs here. There's only, well, not all the graphs, but all the graphs except if you have to interchange black and red to for some of these graphs to reproduce all of the graphs. So let's talk about how these are related to encounters. So these guys here, these both correspond to two encounters. So there's some stretches, and here's one of the two encounters, here's another two encounter. Here's one two encounter, here's another two encounter. And in these two graphs, one of the two encounters is resolved with a black line, here it's resolved with a red line. In this graph, they're both resolved with red lines. This graph here corresponds to the three encounter. So there's three stretches between the three encounter and itself, and this whole mess of red stuff here, which I've drawn here, if you shrink it, it corresponds to a normal three encounter. Now, what you're supposed to think about here is that there's three ingoing black and red boundaries and three outgoing boundaries. So here there's 6 boundaries total. And if you stare at it long enough, you'll see that the pattern of correlation between these boundaries at the beginning and end matches what's going on in this picture here. And so like what we saw in the 2 encounter, there's some extra graphs which are sort of limits of the 3 encounter we need to include. So these are the 2 encounters, these are the 3 encounter. And so all the graphs correspond to encounters, including some of their limits. Now, let's focus on the two encounters for now. And if we take the answer for these graphs, when the energies are large, much bigger than 1 over t, and we have to remember that in this tau scale limit that we're going to take, 1 over t goes to 0, because t scales with e to the s naught. Then we get a simple answer, which is the encounter answer for KE. So the two encounters contribute exactly this, where we've used that rho of e is like square root of e, so we get a 1 over e. So using this, we might try to compute k beta by integrating over energies. But the problem is that this integral diverges at e equals 0 because of the 1 over e. But we have to remember that this wasn't quite valid for energies below 1 over t. That just is an output of the answer if you look at it more carefully. That's because roughly, as I was saying earlier, at small energies, the encounter approximation breaks down. And you need to be sensitive to these resolved encounters where the period differences are large. So what we can do to sort of cheat is just cut off the energy integral at some value proportional 1 over t and say, okay, well, we're only including energies where the encounter answer is valid and summing over those. And we get this sort of answer. There's a constant which depends on exactly how we cut off the energies. And there's a log piece, which we can think of as from the encounter part itself. So this is the cutoff, this is coming from the encounter. Okay, we can also, rather than start with the approximate encounter answer and integrate over energies, we can compute k beta from these graphs by doing a bit more of a direct calculation. Roughly what we want to do is compute the volume by integrating over the lengths of the edges of the graph and plug this into a formula we had a few slides earlier. There you get the exact answer. And we can take the tau scale limit, where t goes with e to the s naught. And we find that the two encounters give us this formula. Now note, this is basically the same thing as what we got from this cutoff procedure, except now this constant that came from the cutoff is determined. So roughly, the whole calculation is giving us the correct answer by treating this low energy stuff exactly. It turns out, if we also look at the 3 encounter graphs, we get a similar formula where the log terms cancel, but these constants coming from the cutoff do not. So adding those together, the log term cancels. You have a t cubed times a constant plus a t cubed times a constant. We get something with a t cubed. That's what we expect in k beta. So the punchline is that k beta is sensitive to these regions of large delta V at small energies. So that means it's sensitive to what's going on inside the encounters. So these graphs, they resolve the 2 encounters and the 3 encounters in these very different looking ways. When we do this cutoff procedure, the theory is saying that what's going on is that the 2 encounters are cut off in a different way than the 3 encounters. So this low energy contribution is different between the 2, no longer cancels. So the reason we're getting this t cubed is because there's a t cubed in the encounters, but the 2 encounters and 3 encounters don't cancel exactly anymore because they behave differently, they resolve differently at low energies. So in periodic orbit language, this is like saying at low energies, when we allow these encounters to become stretched out in some way for long period differences, that's the region where we have to apply this cutoff in the ordinary encounter theory. There's some corrections at low energies in that region. And in periodic orbit theory, we don't know how to treat that regime. It's beyond the linearized approximation of equations of motion. But here in gravity, these graphs are giving us sort of a quantum completion of encounter theory, valid at these low energies. So the last thing I want to say is just let's look at some, say a couple words about higher genus or more general rho of E. So here's a general formula for this k beta in this tau scale limit. The important things here are that we expect a t to the 2g plus 1, and it has a coefficient that depends on rho of E, and it's a polynomial in beta. Okay, so this is some theory-dependent thing. It's a polynomial in beta. What do we do? What do we get if we take these encounters at higher genus and try to apply this cutoff procedure? So a given encounter at genus G, say for like a bunch of 2 encounters or a 10 encounter or something like that, the answer you always get is t to the 2g plus 1 divided by rho to the 2g. And if we plug that into one of these integrals where we cut it off at low energies, we find a contribution like this plus some higher powers of t. So this is like what we saw for the 3 encounter, 2 encounter. There's a log, a constant. But now the coefficient has powers of t we expect in k beta, as well as this whole set of coefficients. So this whole cutoff procedure is giving us the right ingredients for the correct answer for k beta of t, even at higher genus or beyond this Airy model where we have more general rows of E.
Sorry, the log term should somehow cancel?
Yeah, so the log terms we expect to cancel because they don't depend on the cutoff. And so their cancellation is the same thing as the ordinary cancellation of encounters for fixed energy. This constant term does depend on the cutoff. So we don't expect it to cancel.
So for this 2 encounter and 3 encounter, you do see this log piece cancel?
Yeah,
okay.
We do see that. So we see the right ingredients appearing, which is this function of beta. It's pretty non-trivial to reproduce it. But we don't understand why the higher powers of t should cancel, and getting the correct overall coefficient from all these different encounters, we don't know how to do that. So we see the right ingredients appearing in the encounters, but it's difficult to see at higher genus how it all works out to give the exact right answer. So here's some final comments. So in this Airy model, this low energy limit of JT gravity, when we studied this genus 1 thing, where we had this constant term come from this integral of these resolved encounters. And if you look at the integral, it seems like it's coming from a whole big region of the moduli space that doesn't look like encounters. So it doesn't seem to have any good reason to be universal. On the other hand, this spectral form factor, this tau scale spectral form factor having something that's like t cubed at that order times some coefficient should be universal. So it's difficult to see how exactly the treating these low energy corrections and encounters can give a universal answer. So it may be the picture is that in JT or other theories, there's an Airy-like region of moduli space at low energies, which gives the important part of the answer. The rest of moduli space, it's not universal, doesn't contribute. That's a speculation.
So isn't the Airy limit like integrable?
Yes. So I mean,
Then why do you
all these theories that are double scale matrix integrals are integrable in a certain sense. Not integrable in the sense that they're
wouldn't you expect that the Hamiltonian of the corresponding orbit theory or the stadium theory shouldn't have these very encounters trajectories?
So it's integrable in the KdV Hamiltonian is integrable, not the double scaled matrix, the matrix integral. But that's what we want. There's like two Hamiltonians running around. One of them is integrable, one of them is not. And then some other questions we might ask are, we took this tau scaled limit where we had these series where the density states looks like square root of E at low energies times E to the S naught, where we can tune that to be large. For theories like that, we expect we can write down we can take a tau scale limit and write down this convergent genus expansion for the spectral form factor. Are there what are the general class of theories we can do this for? One guess is that maybe we can do this for near extremal black holes in higher dimensions because they have the same square root of E, low energy density states. But for systems that we can't do this tau scaling thing, we can't write down a convergent genus expansion. What are we learning about the plateau from this stuff? I don't know. And that's it for what I have.
Is there any analog of this story in higher dimensional gravity, like in 3D gravity, where there's a UDZ?
Yeah, so I can tell you which parts are known, or to what degree we think each part is universal. So the ramp in the spectral form factor came from a cylindrical geometry in this case. There's a higher dimensional generalization that just comes from you take the two-sided eternal black hole, and you take a nice quotient of it. And there, the whole geometry is purely Lorentzian, not complex, and that's related to the fact that we're looking at Ke, not K beta, and it turns out the boundary time is purely Lorentzian in that case. So there's some subtleties, but you can compute this ramp in the spectral form factor from a universal geometry in higher dimensions. Now about these encounters, let's now ask, can we produce this series of corrections to the ramp in Ke of T for the GOE ensemble? So we might think that there's something like encounters in higher dimensional gravity. So I just told you that there's a generalization of the cylindrical geometry in higher dimensions. Now, this region here, I expect to be locally a lot like that geometry. So when the two orbits are following each other, it's like locally this two-sided black hole geometry. Now, what about these encounter regions here? Is there anything like that in higher dimensional gravity? We saw it show up in this JT gravity. I skipped a slide where I talk about that, in fact. Basically, that region here, the geometry is like the geometry that would appear in the 4-point out of time order correlator computation. And the S and U phase-space separation variables are basically precisely the shock wave modes in the gravity calculation of that correlator. So these encounters, so this at least a two encounter, locally the geometry should, I expect, to look like the higher dimensional computation of a 4.0 TOC. That's conjecture, but just in JT gravity, this region precisely looks like the JT gravity 4.0 TOC. Now, what about higher encounters like the 3 encounter? I expect then that looks like you got 6.0 TOC, so on and so forth. So the ingredients are there for these encounters in higher dimensional black holes, I think. But I don't know how one would begin to actually compute anything like this. No, it's just not
I guess I kind of had a similar question about this, these kind of billiards computations. Can they be done in, like you were saying, in these higher dimensions, or is there a problem with like growth of phase space? Or
Oh
like,
yeah, it's
or how does that go?
So you say like a three-dimensional billiard system
Yeah,
like
sure.
that? Yeah, that can be done. It's just you have more phase space separation variables, but the answers look the same. So yeah,
And does this look like this? This is what looks like the drapes of.
Oh yeah. Like higher dimensions, there's more shockmate modes, and I haven't thought about it very much, but I would expect, but I haven't thought about it very much. But yeah, it is sort of, it's just a side comment. It's a bit remarkable that the answer you expect, this GOE spectral form factor series of corrections, it should be universal. It shouldn't depend on if it's orbits in 3 dimensions, 10 dimensions, or whatever, gravity or whatever. So it's a very universal answer. So it's a bit remarkable that these orbit calculations, they're not sensitive to a lot of the details, like how many dimensions are in. All that stuff can't, like roughly what's happening is all that stuff cancels out because it's this, you always get like a 1 term in a delta function integral. And the ingredients are just 0 modes, factors of t that appear, and the phase space volume suppression. Those are like the only things that appear finally.
So you started with the motivation that we want to see that the spectrum is discrete. It's kind of funny because because the level of this correlator, Siri knows about that. But if one looks at just rho of E, that is continuous, right? And the Siri doesn't. So somehow it's smart enough to tell us that it's a level of correlator, but it's not like QE complete enough to say that's the level of the
whole other can of worms. So here it's because we did this averaging.
Right.
You average out Z by itself, it gets rid of all this stuff. It's like we're computing the variance. So all the things we're studying are corresponding to the variance of the noise in Z. There's some simple, like in JT gravity, there's some ways of incorporating the noise. And, basically, it's like JT gravity is dual to a whole ensemble of Hamiltonians. You can focus on one using the gravity path integral, but I and others think that for ordinary holographic theories, there's something we're sort of missing about how to get the noise.
Because in high dimensions, one expects that gravity itself makes sense without.
Yeah, there should be no averaging.
Right.
Yeah. So that's a whole other can of worms. So yeah, it's a five.
There are these variants of JT gravity which correspond to the other ensemble.
Yeah.
And there the genus expansion truncates to like just cross cap and disk, for example.
Yeah.
So would you expect to make contact with, let's say, GOE or something, or GSE in those other ensembles?
Yeah. So for the Alden ensembles, so here in this picture, there's 3 like sort of non-supersymmetric ensembles. I haven't drawn the GSE, which sort of goes with that. But then there's a universal answer for all those other ensembles.
Yeah.
And so,
so
we would expect to make contact not with these ensembles, but those ensembles, and then we can try to make a tau scale spectral form factor for those ensembles.
But so is there a known encounter theory for those other ensembles?
Oh, known encounter theory. I think so, but I don't know anything about it.
How do I think about k beta of t in the stadium picture? Like you had k e of t, right? But can I think directly about k beta of t in this encounter?
Yeah. So what was important for k beta is that we had some sort of control over the low energies, and to do that, we have to take this tau scale limit where basically the density of states is always large for finite energies, and the random matrix picture is valid. So for orbits, the density of states is proportional to like the size of the stadium. So maybe you can take a limit. The stadium is really large,
But I was thinking that so for k beta you have 2 boundaries. And you fix the length of 2 boundaries. Is there like a physical picture like that for the stadium?
Well, there it's like 2 orbits. So I draw 2 orbits. Like I have this guy, and I'd have one that follows it closely, except for one of his encounter regions. And those are like the 2 boundaries. And like the two orbits follow each other closely, and when they're doing that, there's like you picture that the geometry is like living in between them.
So the wormhole is living between the two.
Yeah.
Sort of.
More questions? If no, let's fill once again. We are going to have a seminar dinner at 5. If you're interested, please tell me.
Thank you so much.
The quick question. So you mentioned this surprising thing. One surprising thing is that in the tau or in the T expansion, that usually you would expect the 3G, but it gets truncated
Yeah.
to the 2G plus 1. So I guess for genus 1, there's nothing to check.
Yeah, exactly.
But you did the similar computation for higher genus, and you see
So
the convolution does not appear when you just look at encounters, or what is the conclusion?
So at genus 2, which is the only case it gets a little more close. At genus 2, like you have a 5 encounter, say, and the 5 encounter comes with a t to the 6th, with the answer in the end is a beta to the t to the 5th.
That's right.
So it has to cancel between the encounters.
Yes.
We don't have a good understanding of why.
But you say the Airy limit it's kind of explicit what the individual contributions are.
Yeah.
From the graphs.
So
So
there's a lot of graphs.
Yeah.
That's the problem. So at genus 2, there's like a lot of graphs.
I see.
They can all be classified into encounters, and they're like sort of limits, but there's a lot.
But is there a way to compute their contributions like in a recursive way?
I would hope so, but I don't know.
Something like a topological recursion.
Yeah, we had that a little bit. Is there like a simplified topological recursion? And
that's what you expect, right?
Yeah. We didn't think about it too long, but we didn't make any progress.
I see. And just a question like precedes that. Can you explain again where does this 2G plus 1 truncation come from? What was the argument that it has to be truncated?
So if you do white k beta as the integral over this rampant plateau.
Yes.
Over energy.
This mean that
you
expand this mean in terms of the theta and delta.
Yeah. So you always get that, but like for JT gravity we check to like genus 11 or something like that, but it's correct. Just using topological recursion. So the argument would be based on this main function.
Right.
We've checked. That's like not a proof. We checked it to high genus. So I believe that.
Okay.
But yeah, like an argument in terms of the geometry, to be honest.
Okay. Thank you.
Yeah, I was curious. I thought there were, I don't know the story too well, but I think there was maybe some non-perturbative negativity for the GT model.
Negativity in the density
of states?
For ordinary JT, there is a so ordinary JT, there's a effect which is non-perturbative in the genus expansion, which is like there's an instability, not a negativity. So maybe there's some models that are closely related that I think have some negativity problem, but not ordinary JT. And I'm pretty sure not the GOE version of JT. The other thing that I know about is that in because
I thought this was something that like Clifford Johnson was worried about, like making them perturbatively stable.
Yeah, so there's I think one of the things that I know that he was worried about is Stefan. It's like you can think like JT gravity is like you compute density states are like solving for a minimum of a bunch of like repulsive particles in a potential. Those are like the eigenvalues. So the eigenvalues, they live in a potential roughly, which is like something like this, and here this is.
So these would be like the eigenvalues of the matrix.
Yeah, these are the eigenvalues of the matrix.
Yeah.
And so
they could escape, I guess.
Yeah, so the potential is like unbounded from below. But so perturbatively they stay here, then the whole genus expansion keeps them in here, but there's a non-perturbative effect. Which they go down. you can actually, so this has an action e to the minus e to the s naught. This goes to 0 in this tau scale limit.
Yeah, that's okay. That's
Yeah.
okay.
So you can, in this tau scale limit, you can forget about it. It's not important.
But if you're interested in this at finite, like you're interested in extending this outside of that, so you'd have to worry about these sorts of effects.
So there, like Clifford Judson studied like variation of JT where it's not a problem.
Right.
So it's like I think probably there's ways to talk about all this stuff where from the starting point you start with a better model.
Right, but it's just the connection that outside of this like scaling limit that you all took, you all have to be worried about stability.
Yeah.
Because you're interested in like the lowest part of the spectrum, right?
Yeah. So if you're interested in like very non-perturbative effects, always being around, not killed, then it's important. But then you can like use super symmetric JT gravity or something like that. And it just makes the genus expansion more complicated, I guess. But I would expect not much would change qualitatively related to the genus expansion.
Okay, yeah, because he was also seeing these like wiggles, right? I don't know.
Yeah,
so
so
I wonder
like,
if they would show up here at all.
Yeah, so
I guess you have the density of states already in your expansion.
There's like sort of two things. So just one is like rho of E has like the plus a bunch of perturbative corrections plus something that's oscillating. Or no, it's more complicated than that. But it's something that's oscillating. And what it's saying is that the eigenvalues tend to live at the peaks of the oscillations. All that sort of, okay, so I wrote this formula for the spectral form factor in terms of the density of states. But in the tau scale limit, where all that stuff sort of goes